So to start with, let's talk about the ranking. So ranking has been at the core of applied machine learning. If you want to develop something, develop your model, basically the model is the ranking is the only thing that you care about. And if you think about all these LLM news or hypes that you read before, like people basically rarely report anything about the scores. They only tell you about the ranking, something like I just outperformed ChatGPT on some task, or I just achieved number 1 on some leaderboard. So it's all about ranking, and ranking is all you need. And a good ranking is the goal of benchmarking. But it's not. Yes. But when it comes to large language models, it's a little bit tricky because large language models can solve many tasks. And then the question is like, which ranking should we look at? Because each task gives you a ranking, right? So a nice idea here is to use multitask benchmark. Basically, the idea is quite simple and intuitive. It's just to evaluate them on everything, right? Here's an example. Here, like each row stands for a model, and each column stands for a task. So this is a multitask benchmark. But here's the problem. The first problem is the tasks that don't agree with each other. So each task actually gives you a different ranking. So here are 2 tasks. They're actually kind of of the same type. Like both of them are like question answering tasks. But you can see that they give you very different rankings. And in our previous work, we actually made an analogy between the multitask benchmarking system and the voting system. Here is the analogy is like each task is like a voter and each model is like a candidate. So essentially, it's just like each task is voting which model is better. And the multitask benchmark is just trying to aggregate all the preferences and give you like one ranking. But here's the classic theorem in social trust theorem called Arrow's impossibility theorem. It basically says it's hard to aggregate many rankings into one good ranking. To put it in the context of multitask benchmark, our result shows that there's an inherent trade-off between the task diversity and ranking stability in multitask benchmarks. So the message here is like, if the tasks are different, which is desired because you want to measure different things. So when they're different, you just cannot get one robust unified ranking out of it. So that's the key takeaway. Okay, these are probably a little bit too detailed. We can probably skip this for now. But yeah, that's the first problem. But here's something that makes it even worse, which is about the cost of benchmarking. So, LLMs are like pretty big right now, and evaluating them could also be very costly. For example, evaluating such a model called Bloom on the benchmark called Helm requires 4,000 GPU hours, which is a lot, especially for research labs in academia. So people have proposed like multiple methods for like somehow efficient benchmarking. But our recent work shows that these methods actually they very often fail at the frontier new models when these models are better than existing ones. So it seems that we're in a pinch right now. So first of all, we know 2 things right now. First of all, we see that rankings are inconsistent, and you cannot get one good unified ranking out of it. And second one, computing many rankings is very costly. But actually, there are some good news. So first of all, the ranking inconsistency is actually an artifact of how they're trained. And our recent work shows that we can actually remove the artifact and recover highly consistent rankings. So first of all, where does this ranking inconsistency come from? So our colleague Ricardo and Gloria and Morris had a previous work called training on the task. So it says that when the models are released, they have actually done a different level of preparation for different tasks. So this says like some models have studied to the test while others haven't. And as a result, you can expect different performances on different tasks. And so there is an inconsistency on the rankings. And this is called training on task. And natural idea here is what we call train before test. So what we want to do is like if they have done different preparations, so right now what we want to do is to give them the same amount of preparation before we evaluate them. And we call it train before test. So basically we just give each model the same benchmark specific fine-tuning before we evaluate them. And the results are amazing actually. So if you take a look at the left figure, so this one is when it was direct evaluation, and you see that the two rankings are super different. But when it comes to like train before test in this figure in the middle, it seems that the rankings are in these two tasks are actually very consistent. And in our work, we actually evaluate train before test on 24 benchmarks. And it turns out that the rankings on all these 24 benchmarks are all very consistent with each other after you use train before test. And actually here's like another figure which shows these 24 tasks. The blue bar shows the ranking consistency of this task with respect to all the others. And the yellow bar shows the ranking consistency in the train before test. And turns out that, as I said, it was a little bit inconsistent before, but it was quite consistent after we do train before test. So this is an interesting idea. It says like you can get some consistent rankings after you do train before test. And yeah, so here's another result. Still about the ranking consistency. So previously, you can also categorize all these tasks into different categories or different types because benchmarks are like, sorry, each benchmark is supposed to mirror a different thing, but some are like mirroring the same thing. So we classify them into 5 categories. Sorry, 6 actually, like a lot of categories. And it turns out that like the benchmarks within the same category still disagree with each other very often. That's shown in the left figure. And also categories also don't agree with each other, of course. But if we do train before test, then just basically everything agrees. Everything agrees with each other. It's kind of like an interesting result. Yeah, so here's another interesting thing. It's like it's about the perplexity. So what is perplexity? Perplexity, you can take it easy, like you can just take it as the training objective of large language models. It's like just how you train large language models. That's the objective. It's kind of like very old school metric that people basically have already abandoned. But actually we show here, like if you do train before test, the perplexity rankings are also very consistent with downstream rankings as shown in the bottom figure. But it wasn't the case when you do direct evaluation. This is kind of like a good result because it tells you that the training objective is now consistent with your test time evaluation results, which is desired, right? Because like you somehow expect that when you have a lower training loss, you have some better, evaluation results. So this is somehow also like the benefit of train before test. The one last thing I want to mention is like we can also do like low rank decomposition for the whole benchmark result. So still here's such a matrix. Each row stands for a model. Each column stands for a benchmark. And the entry is just the corresponding model's performance on this benchmark. And we just do a low rank decomposition to it like this. And interestingly, it turns out that this whole matrix, like 24 times probably like 60 times 24, sorry. It's actually a very low rank. It's basically rank 1, actually. You can see that the PC1, the first principal component, actually explains like 92% of the variances for the whole matrix. So it says that if you do train before test, the whole performance, the model's performance on all the tasks are actually dominated by only one factor. And our results also show that this factor is also highly correlated with model scales, but I didn't put the result here, but yeah, we do have this result. Yeah, so I guess that's the major thing I wanted to say, but yeah, this is actually this is the correlation between the PC1 and the model scale. Yeah, it's also very correlated. So I would say PC1 actually stands for some sort of general capability. useful for all the tasks. And because also we also show that all dimensions of PC1 is positive. Well, but actually, I also would like to mention that the interpretation of the PC1 here is actually kind of open. You can say it's like the general capability, or another potential interpretation is we can call it like the model potential. Because if you think about what train before test is doing, it's just mirror the model's performance after some learning, right? You can say that's basically the definition for potential. It's like what you would perform after you do some training. So I would say train before test somehow mirrors model potential. And if we take this perspective, then we actually have like demonstrated three things. First of all, the model potential rankings in any benchmark extend to the others, which means that you can just evaluate the model potential in one benchmark, and you can expect this ranking would also apply for any other benchmark. And then it also says the model potential highly correlates with the perplexity of models, which also correlates with your training objective, which is nice. And the last one, we said model potential is actually of rank 1 because it's dominated by one factor. Okay, wait. So here's the takeaway. First of all, ranking is all you need. And then the current benchmarking is broken for LLMs. But here's a fix, which is to use train before test. Yeah, thanks.